In this video, we're going to go ahead and cover the last part of Unit 9, Sequences, Series, and Probability, 9.7, Probability. So this is probably the one that you're the most familiar with. Basically, it's kind of like, what are the odds of this happening out of this many events or times or whatever? So we have that the probability of an event is based on a few things, few definitions. We have an experiment, which is basically any happening for which the result is uncertain. So just your basic definition. The outcomes are all the possible results of this experiment, so of said experiment. And then the set of all possible outcomes is the sample space. So all these outcomes are like elements of this thing called the sample space. An event is any sub-collection of the sample space. So the event is kind of like when we're saying, what are the odds of getting a 1 out of 6? 1 would be the event. Okay, so that's what that referred to. Let's look at the first example, which is actually worked out for us. We do have a few examples here. Some are worked out because of the time. So for example, number 1, we have find the sample space for the experiment. And here is the experiment. You toss a coin twice and a six-sided die once. So if you do that, what are the possible outcomes that we might get? Okay, so here's what I did. As I went ahead and first of all, I kind of labeled what this means. So I do HH, that means both heads. HT means heads, tails. T and T is both tails, and then T and H is tails and heads. So that's what those letters refer to. So here is our coin sample space. If you toss if you toss a coin twice, the chances are you can get heads, heads, tails, 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 heads, and those are the only combinations we're going to have with tossing a coin twice. The sample space for the die is basically 1 through 6 because it has 6 sides and each of them has 1 dot, 2 dot, 3 dot, all the way up to 6. So we have 1 through 6. So we have 6 events in this sample space. So how do we find the total sample space? Well, we just combine them. We see what are all the possible combinations of these things happening. So for instance, we can have 2 heads and the number 1, so that's the first one. We can have 2 heads and number 2, that's the second one, 2 heads and number 3, and so forth. So you have basically, you can get 2 heads and then any of these numbers, which is a total of 1, 2, 3, 4, 5, 6 different events. And then you move on to the next one. So we could also have where we get heads and tails and the number 1, heads and tails and the number 2, and so forth. You kind of get the idea. So we kind of combine this with all of this with all of this, and it gives us a total of 24 possible event outcomes, which is the same as saying 4 times 6. Yeah, so we could have just done that as well, but I wanted to show you the actual outcomes in the sample space. Okay, so that is it for this one. Let's move on to the next one. This was an example of finding the sample space. Okay, so next part is the probability of an event. So the probability of an event, if we have an event E, has N of E equally likely outcomes, and its sample space S has N of S equally likely outcomes, then the probability of this event E is the following. So this means probability of E is basically equal to the chances of E happening, so whatever amount of times we have it in the space, divided by the total space. That's kind of what this is. Think of it like part over whole. So let's look at example number 2. It says you toss 3 coins. What is the probability that all 3 land tails up? Okay, so the chance of, first of all, the chance of a coin landing tails up is 1 out of 2, right? We know that that's going to be 1 out of 2. So we can think of it like the following. P of E equals 1, okay, out of 2. And that would be kind of like your first toss. The second toss, you still have a 1 out of 2 chance. And the third toss, you still have a 1 out of 2 chance. So it's a total of 1 out of 8. That's it. That is our answer for this one right here. Okay. And if you wanted to do that, the sample space, we could. I'm not going to do that just because I don't really want to take too much time. But basically, an example of the sample space could be like, so we had S equals, we could get, let's see, heads, heads, and heads for one of them. We could get heads, heads, tails, and so forth. And you get the idea. So there would be a total of 8 different 8 combinations, okay, when you do all of them. And the one that we're looking for is tails, tails, tails. So there's only one event out of 8. And again, that goes back to what we have here. Okay, let's look at it, the second part of example 2. It says you draw one card at random from a standard deck of 52 playing cards. What is the probability that it is a diamond? Okay, so in this one, you kind of have to, you do have to know a little bit about cards. We know that the diamond, there are 13 of them. Okay, so let's do it like this. There are 13 diamond cards, and there's a total of 52. And I mean, again, I could do the entire sample space. That's going to be a lot of things to write down, though. So I'm just going to go with the fraction for this time. And if you reduce this, you just get 1/4. So the chances of getting a diamond card out of a random standard deck of 52 playing cards is 1/4 because there are exactly 1/4 of the stack are diamonds. Okay. And that is basically it for that one. Okay, so let's look at the next one. These are going to go kind of fast, hopefully. Sample number 3. Show that the probability of drawing a club at random from a standard deck of 52 playing cards is the same. So we're trying to prove something here. It's the same as the probability of drawing the ace of hearts at random from a set of 4 cards consisting of the aces of hearts, diamonds, clubs, and spades. Excuse me, I'm a little sleepy today. So we have two things we're comparing. Let's kind of look at the first one here. We want to see the probability of drawing a club at random from the standard dark deck of cards. So for the club, we know that. So we'll do like this. We'll do P of A. We'll kind of the club. This top part will be A, and the second part will be B. Okay. So for the club, we know that there are 13 clubs, right? In the whole 13 times that this is going to come out in the deck of cards out of 52, which is equal to a fourth. So we're trying to prove that this is going to be the same as the other one. So let's see. Is the probability of drawing the ace of hearts. So now we're looking for the ace of hearts. Okay, let's make our heart nice and lovely there. Ace of hearts. So, and it says from a set of 4 cards. Now we only have 4 cards. And those 4 cards has the aces of all the other ones. So we have, we have the card with the hearts. We have the card with the, oh, I forgot what they're called. The spades, I guess, what it is. The one with the clovers. It's a horrible clover. And then, what is the last one? I guess the club. I don't remember what it looks like. I'm having a total moment right now. But anyway, there's the fourth one. So we want, and these are all A's. Okay. Oh, diamonds, diamonds. What am I thinking? The diamonds. There you go. So we want the ace of hearts. So well, again, there's one out of the 4. So you could think this could kind of be like our sample space, actually, right? So again, we just have the probability, I'm going to call it B just to make it different from this one, is going to be 1 out of 4. And they are the same. Yeah, my arrows are not that nice there, but you get the idea. Okay, so there you go. Easy, easy, easy. Number 4, we have in Texas's Cash 5 Lotto game, you choose 5 different numbers from 1 to 43. Okay, get this a little bit straighter. If your 5 numbers match the winning numbers drawn in any order, you win. So, I mean, a basic lotto. If you get the same numbers that are randomly drawn, you win the lottery, right? Lucky you. What is the probability that you win? Well, we know that the odds are actually stacked against us in this game. So how do we do this? Okay, so this was kind of a combination of what we did in the last subunit, where you have a total number of elements. So in this case, 1 to 43, we have 43 numbers to choose from, and you're going to choose 5. So I kind of mentioned this notation, and choose R. Yeah, remember this, and choose R, where it's basically a combination. Yeah, it's a combination where the order does not matter. So this is the same as C and R, remember the combination, which in this case would be C, and then we have 43 numbers, and we're choosing 5. So the formula goes 43 factorial over 43 minus 5 factorial over 5 factorial. Okay, so that's going to give us 43 factorial. Oh, well, that's okay. 43 minus 5 is 38 factorial over 5 factorial. So that means I have to expand this all the way to 38. So 43 times 42 times 41 times 40 times 39 times 38 factorial all over 38 factorial, 5 factorial. This is gone, so we're left with 43 times 42 times 41 times 40 times 39 all over 5 times 4 times 3 times 2. And I'm just going to calculate that real quick. I'm not going to do it in my head because, well, those are some big numbers and we don't want to spend all day here now, do we? As much as, math is fun. Let's see, let me do that real quick. 43, 2, 41, 40, 39. Okay, so for the top, I'm getting this humongous number, 2,665,650. Yeah, okay. And on the bottom, I believe that's 120. 5 times 4 is 20. 20 times 3 is 60 times 2 is 120. Yes, 120. So I remember that one at least. So if I divide that by 120, I get 222,138. So 222,138. So this is all the possible combinations, right, of these numbers, which is kind of a lot. Now remember that the probability, we're going to call it P of E, is the chance that you win. So the chance that you win is basically that one event that you win. They have to be the exact number. So it's going to be one out of the total. So 222,138, 222,138. And those, my friends, are your odds of winning the lottery with the cash five. Okay, let's move on. So we have the next one, which is actually done for us because of, again, the time. So another definition, mutually exclusive. Mutually exclusive is when two events, A and B, from the same sample space have no outcomes in common. So in other words, if you were to intersect them, which is what this means right here, A intersect B, it would be zero. They would have nothing in common. One way to think about this is like a Venn diagram. I don't like using Venn diagrams too much because honestly, they're one of my weaknesses in me personally in math. But you're thinking it's basically everything over here, and they share nothing in common. So this part in the middle would be empty. Okay, that's what this means. And it tells you right here, intersection of A and B equals zero. So with that in mind, let's define the probability of the union of two events. So this is the intersection of two events. This is the union. The union is when you put them together, okay? So if A and B are events in the same sample space, then the probability of A or B occurring is given by the following. So another way to think about the union is it's kind of like an or statement, okay? If you remember back from geometry, a little bit of a logic there. So A union B is if we do the probability of this, it's basically going to be your probability of A plus the probability of B minus the intersection. Okay, and I'll show you we're going to do an example that kind of shows this. It does say if A and B are mutually exclusive, that means that the union is going to be just these two added together because what's going to be zero, so it's not going to really matter. Let's look at an example. It says you draw one card at random from a standard deck of 52 playing cards. What is the probability the card is either an ace or a spade? So it has to be one of the two. Okay, so here's the solution for this one. And I kind of did this in two pieces here. Well, three pieces. We have the event of the ace. So the aces, there are four aces in the entire deck, right? There's one of each sign, one heart, one spade, one club, and one diamond. Total four. So 4 out of 52, which is equal to 1 over 13. And I'm going to leave both of these here just because, well, you'll see in a bit. Now, the event of a spade is going to be 13 out of 52 because now we're talking about all the spades. So remember, there are 13 of each type of uh of sign. I'm not sure what they're called, but yeah, there's 13 spades. So 13 out of 52 is 1 over 4. Again, I'm leaving both of them because we're going to have to add them. So we might want to use the 52 so we don't have to do common denominators, right? But I wanted to show you what it's equal to anyway. And then the intersection is basically where you have both happening. So we have one spade that is an ace, right? So that means out of the whole deck, you do have one card that is both of these. It's both an ace and a spade, which means that the intersection of these two, which is that upside down U looking thing, is 1 out of 52. So we just plug all this into the formula. like so, where I take P of A, P of B, add them, and subtract P of A intersect B. So that's going to give us 4 plus 13 minus 1. They all have the same denominator, so we can do that. 4 plus 13 is 17, minus 1 is 16, so 16 over 52, both divisible by 4, so it's 4 over 13 as a fraction, or if you wanted to get the decimal equivalent, or almost equivalent, because it's actually an approximation, it'd be 0.308. So there's a 0.308 chance that you will take, you would get either an ace or a spade from this deck of cards, okay? And that is it for that one as well. So there's the whole problem if you want to take a copy real quick. Let's look at the last one we're going to do together. I'm sorry, there's two more we're going to do, but the last one is actually worked out for us. So this one's not. This is the probability of independent events. So if A and B, excuse me, are independent, then the probability that both A and B will occur is P of A and B is P of A times P of B. So kind of what we've already seen, you just kind of multiply them together, and it can be extended to, P of C, P of D, and so forth. Let's look at example 6. We have a random number generator selects two integers from 1 to 30. Remember, an integer is just a whole number that's either negative or positive, and it includes 0 as well. But in this case, we just want 1 to 30, so you're thinking the 30 numbers. Okay, what is the probability that both numbers are less than 12? So let's do this. We're going to say P of A, which is our first number. Well, the chances or the probability that it's less than 12 is the numbers 1 through 11, right? So you have 11 times that could happen, the numbers 1 through 11, out of 30, because there's a total of 30 numbers. P of B is going to be our second number, and it's asking basically for the same thing. So same exact fraction, yeah? So to get the probability of these things happening, we say that P of A and B is going to be P of A times P of B. So 11 over 30 times 11 over 30, which is 121 over 900. And that is it for that. Okay, nothing fancy. Okay. Last one, we do have one final definition here. It says the complement of an event A is the collection of all outcomes in the sample space that are not in A. So it's kind of like saying if A is one thing, the complement is everything that is not that thing. Like the opposite, okay? Probability of a complement, this is how you notate this. Let A be an event and let A prime, this means A prime, that's how we say it in mathematics. A prime be its complement. If the probability of A is P of A, then the probability of the complement is P A prime is equal to 1 minus P of A. In other words, if the probability of P of A was 1/4, let's say whatever the event was, the chances of getting this is 1/4, then the complement would be 1 minus a fourth, which would be 3/4. So it's whatever completes it to that 100% to 1. So I did kind of squeeze this one in here because I didn't want to go to another page, but here it is. It says a machine averages one faulty unit for every 500 units. What is the probability that an order of 300 units will have one or more faulty units? So it's kind of a tricky one because we have to get the probability based on a previous example. So what we're doing here is we kind of went backwards. We said, well, the probability of, since we want the one that's faulty, we're going to find the probability of not faulty. So let's call P of A not faulty, and it's going to be based on this 500. If one unit is faulty for every 500, then that means that 499 units are not faulty for every 500, okay? And if we have an order of 300 of these, well, you're thinking this 300 times. So instead of, I'm not going to write it 300 times. I'm going to raise it to the power. It's just easier to do. So I plugged this into the calculator, just simple calculation. Well, not simple, but simple input into the calculator. And it gave me 0.548. So the chances of it being not faulty are, they're pretty good. They're 0.548, yeah, 300 times. So that means that, well, they're better than half, a little better than half. Well, ish. We'll just leave it at that. It's not too bad. which means that the complement of this would be 1 minus this number. So 1 minus 0.548 is going to be 0.452. And these are the chances that you're going to get a unit that is faulty. And believe it or not, guys, that is it for this video. So if you have any questions, as always, please let me know.